The purpose of this video is to look at quasi 1D or nearly one-dimensional flow in a nozzle, right? So we have a flow going from left to right in this nozzle, and we are looking at quasi one-dimensional flow in this nozzle. Although the area of cross-section seems to change as I go from left to right, we're going to treat this as quasi one-dimensional flow. Let's think about the conservation equations in this case. All right, so if you have steady flow, then basically the conservation of mass statement, because now the area is changing, simply says rho AV equals a constant, right? So I can take the differential of this, d of rho AV, clearly has to equal 0. Now, in order to take the d of rho AV, I can write that as d rho times AV would be one term. The second term would be dA times rho V, and the third term would have a dV times rho A equals 0, right? And so we are allowing the area to change, and that's what we mean by quasi one-dimensional flow over here. Now, if I divide this equation through by rho AV, every term by rho AV, let's see what we get. Okay, so the AV's cancel out over here, the AV's cancel out, I'm left with d rho over rho. So I'm going to get d rho over rho plus dA over A plus dV over V equals 0, right? Another way to read this equation is that the fractional change in density plus the fractional change in area plus the fractional change in velocity have to sum to 0, right? So if something is positive, something else has to be negative in this expression for these three terms to sum to 0, right? So that's the meaning of this expression. And remember, there are no other assumptions about the nature of the flow except sort of that it's quasi one-dimensional. Okay. Next, we look at conservation of energy equation. I can write the conservation of energy equation in the following form as H plus V squared over 2 equals a constant, right? This is simply the stagnation enthalpy being constant in the flow, and the assumptions being that there's no energy added into the flow in the form of either work transfer or heat transfer. So that's the only assumption at this point. Now, if I take the derivative of this expression or take the differential of this expression, I'm going to get dH plus, I'm going to get 2V dV divided by 2 equals 0. In other words, dH plus V dV equals 0, and we label this as equation 2. So equation 1 is a statement of conservation of mass. Equation 2 is a statement of conservation of energy in its differential form. Let's recall what's called the Gibbs equation, which we saw in an earlier video. The Gibbs equation basically tells us a relationship between entropy change, and pressure change, right? So TdS is dH minus dP over rho is what Gibbs equation tells us. Now, if you add an additional assumption that the flow is isentropic, that means ds equals 0, right? So there's no change in entropy, so we made the assumption, invoked the assumption that the flow is isentropic. So once we do this, Gibbs equation basically tells me dH will be equal to dP divided by rho. Let's label this as, let's see, we're going to label this as equation 3. Okay, so now I can substitute equation 3 in equation 2, and let's see what we get. All right, so in equation 2, notice we have this dH term, and so the dH term can be written as dP over rho via equation 3. And then this next term is V dV equals 0, right? And if you think about this, this is really Bernoulli-like equation with a very strict statement that I got to make, that Bernoulli goes on further by assuming rho is a constant. Here we are not making that assumption, right? Here we're not going to make this assumption. And then we also have dP equals c squared d rho, and this comes from the speed of sound, if you recall the video associated with that. All right, so I'm going to take this expression for dP and stick it in the equation above. And let's see what we get. So dp can be replaced by c squared d rho divided by rho plus v dv equals 0. Or I can solve for d rho over rho. It's going to be negative v dv over c squared. If I go back to equation 1 and rearrange it, I can write down dv divided by v equals negative dA over A negative d rho over rho. So I move the dA over A and the d rho over rho to the right hand side of that equation. So I can write this as minus dA over A. And dv rho over rho, we got an expression for that, so we can stick that in. So it's going to become a plus v dv over c squared. So from here, I got dv over v times 1 minus, I'm going to write that as v squared over c squared equals minus dA over A. So what I've done is I've taken this term v dv divided by c squared over to the left hand side of this equation along with the dv over v. So I've factored out the dv over v times 1, which is how I get this term. And then this term with the negative sign moved over to the left hand side is dv over v times v squared over c squared, right? All right, so I factor the dv over v, and that's why I get a v squared term over here, right, to account for the v in the denominator back here. All right, so what does this lead up to? So I can rearrange this and write down dv over v equals dA over A times 1 over m squared minus 1. So I can work in the definition of the Mach number. So remember, v over c is simply the Mach number, right? And that's how I get this result. And let's label this as equation 4. So this is the fundamental equation we get from applying the basic ideas and assuming isentropic flow through variable cross-sectional area quasi one-dimensional flow. What are the implications? And the implications are pretty amazing. All right. So let's say if the Mach number is less than 1. So Mach number less than 1, we understand that to be subsonic flow. And so if the Mach number is less than 1, m squared minus 1 is going to be a number which is less than 0. So dv over v would be equal to some negative quantity times dA over A. So in other words, if dA is positive, dv would be negative, correct? So if dA is positive, that means dv would be negative. Now what does dA positive mean? dA positive means as I move downstream, the area is increasing, so the area of cross-section is increasing, so dA is greater than 0. And if dv is less than 0, it means the velocity is decreasing, right? So as the area of cross-section is increasing, the velocity will decrease, right? And so if I have this kind of a section, this tells me that as the area of cross-section is decreasing over here, then the velocity has to increase. In the analysis we did here, we are looking at the reverse situation where, let's say, the nozzle looks like this. So as the area of cross-section is increasing, we expect that the velocity is going to decrease. All right, that's consistent with what we understand about incompressible flow. However, let's look at equation. I'm going to copy equation for one more time. dv over v equals dA over A times 1 over m squared minus 1. Let's assume Mach number is bigger than 1. If Mach number is bigger than 1, then m squared minus 1 is going to be a quantity which is going to be bigger than 0. In other words, the left-hand side and the right-hand side would have the same sign. Okay, so dA and dv have the same sign, which means if dA is greater than 0, this would imply dv is greater than 0, right? So in other words, as the area increases, right, and let's imagine this kind of a cross-section going from left to right, the area is increasing. Then according to this, if the Mach number is bigger than 1, then the velocity continues to increase. So which is kind of counterintuitive. And that's the beauty of compressible flow, is that as the area is increasing over here, the velocity is actually increasing over here, right? And so what we understand is for a flow to go from subsonic conditions to supersonic conditions, we essentially need a nozzle which has to be shaped something like this. It's got to have a converging section where the fluid is accelerated, and for it to accelerate beyond this point, where technically this is called the throat of the nozzle, and at the throat of the nozzle, the Mach number achieved would be 1. Again, we are looking at the idealized situation. So the velocity continuously increases and reaches the speed of sound at the throat. And then for the fluid to continue to accelerate, it turns out that the area has to increase, as shown by the analysis over here, right? When the Mach number is bigger than 1, then dV and dA have the same sign. And so area has to increase, and then the velocity is going to continue to increase. So this is what rocket nozzles tend to be shaped like this for this reason, right? And we can come up to this amazing conclusion just through the simple quasi 1D analysis. So that concludes, and that's sort of the purpose of this lecture, is to show you the area Mach number relationship.